Okay, so we're going to look at various ways to measure the center values of data. There's more than one way to look at center. The one you're most used to, is the average, called the arithmetic mean. Or just the mean for short. It has a variable, x, with a bar over it. X being the variable being measured, and the bar meaning that you've taken the average or the arithmetic mean. You will be doing this a lot this year, so let's look at some shorthand notation for it. Let's start with the sum of all the elements. So remember, this is the Greek letter E, which generally looks like this. It's not the way I draw it. Takes me too long to do that, but sorry, it's not an E. It looks like an E. It's the capital S. It's the Greek letter sigma, and we use S to represent the sum. So first thing you're going to do, if you remember calculating the average of things, you add up all of the values and then divide by how many values there are. So this means to add up, or to sum, take the sum of all the values. Now xi represents all the values because shorthand says we're going to start with whatever the first value is, not the number one, but whatever the first value is for an element in the set, and we're going to add every single element until we get to the nth value. So this actually says to take the first value, add to it the second value, add to it the third value. Addition, remember, is commutative, so it doesn't matter which order you add everything together. It just means you want to make sure you get every element exactly once. And then you keep adding until you run out of values to add. Oops, I meant for that to be an n. So I want the nth term. And then remember to take the average. We add all the values up and then we divide by how many there are. But how many are there? Well, if we look here, we can see that once we add them all up, we're talking about n values. So we're going to divide that by n. Have to do that on both sides. And when we're finished, what we have is the shorthand formula or equation to find the arithmetic mean, or x bar. Now, this is going to give you the average value for your set of data in your experiment. Often there's a population value that you either extrapolate from your experiment or that has already been determined before, and you can compare your data to it. When we're talking about this, the average for the population, we use a variable called mu, and that gives us the population mean, or the mean of the population. Where x bar is your experimental mean. Or sample mean. So experimental can also be the sample. All right. So let's do an example. Let's say we've run an experiment and our measurements are 5, whoops, that's not true, 2, 9, 11, 5, and 6. All right, so we want to find the arithmetic mean, and then we're going to compare it to a dot plot and see if it makes sense. So the arithmetic mean, first thing we want to do is determine what is our n value. How many elements do we have? This one's super easy because n equals 1, 2, 3, 4, 5. And then we want to find the x bar, or the arithmetic mean, which means we're going to look for the sum of elements from the first to the 5th. And we'll divide all of that by n. So in the numerator, we're looking at 2 plus 9 plus 11 plus 5 plus 6. And in the denominator, n elements, 5 elements, is divided by 5. So let's see. 9 and 2 is 11, and 11 is 22, and another 11 is 33. Stick that in my calculator and I get 6.33. 6. So unlike algebra, where what we like to work with is the improper fraction, in statistics we're going to work with the decimal. This calculation tells me that the very average, the very center of this data is 6.6. We're going to look at it on a dot plot, see if it makes sense. So a dot plot is really representing on a number line how many values and where those values exist. So I don't care about the whole number line, negative infinity to positive infinity. I only care about representing the values that I have in my data set. So I can make my smallest value 2 and then represent the number line until I get to 11. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if this is 11, then if I plot each data point just with a dot, so it's sort of like I'm stacking pennies on top of a balance. So I know I have a 2, I know I have a 9, an 11, a 5, so 2, 3, 4, 5, and a 6. Now, my calculation tells me that my balance, or the place right in the center of all my data, should be right about here. And now look at it and see if that makes sense. And it does, because even though I have 3 data points here, they are super close to the center, and I only have 2 data points here, but they're farther away. So these 2 that are really close aren't going to have, when you think about how a scale or a balance works, they're not going to have as much weight pushing down if this were an actual scale, right? So if I had a scale here and I was trying to see if my number line balanced half and half, these 2 points are farther away, and so they hold more weight or more value. So just by looking, I can say that I do think that my value of 6.6 as the middle, or the arithmetic mean for this set of numbers, makes sense. All right, so arithmetic mean is one way to measure the center of data. Another way is to find the median. Median just means not really caring what the values are. We want to find the very center of data where half of the values are smaller than that. 1, 2, 3, 4, 5, 6. So I have 6 values that are smaller than whatever the median is, and 6 values, these are meant to represent bigger, and 6 values that are bigger. We don't care what they are, we just care that all of the values on the right-hand side are bigger than this median number, all the values on the left-hand side are smaller, and the set is divided exactly in half. So let's look at an example of this. Let's use the same data that we used before and break it into 2 parts, where all of the parts on this side are smaller and this parts on this side are larger, which means, I don't know if you can hear this, but Puppy Porter is going to town on a plastic bag under the table. Hopefully it's not too distracting. It's distracting the living daylights out of me, but that's okay. I can continue. So first thing I want to do then, since I want all the smaller elements on this side and the bigger elements on this side, I'm just going to order them from smallest to largest. So I have 2, 5, 6, 9, and 11. And now look for the very middle, where I have 2 values that are smaller than 6, and I have 2 values that are bigger than 6. So I can say that the value 6 is the median. So M, we just use the letter M for median, and the median equals 6 in this case. Now, you don't always have an odd number of elements or measurements. So let's look at another example where you have an even number of measurements and see how to find the dead center for that. So this time we're going to use 2, 9, 11, 5, 6, 27. Just adding one number to the set that we had before. Okay, this time again, order them from smallest to largest. 2, 5, 6, 9, 11, and 27. So now if I start at the other end, and I always do this by like slashing through, so I take one element off of each end, and then one off of each end, and then one off of each end until I get to the middle. Well, that didn't work for me because I just scratched them all out and I have no middle value. So instead, I'm going to do the same thing. I'm going to take one off of each end, take one off of each end, and then when I get here, I notice I have two. No worry. All I have to do is take these two and find the arithmetic mean. So 6 plus 9 divided by 2. 9 and 6 are 15 divided by 2, which is 7.5. So for this second data set, the median, I use the mean to find the median, but the median value is 7.5. That means exactly half of the data falls smaller than 7.5 and half of the data is bigger than 7.5. And the last measurement for center that we'll look at today is called the mode. And the mode really just is what shows up the most. What value do you see more often than every other value in your set? So if we look at our original set here, there is no mode because every value shows up exactly one time. But if I change this set in only one tiny way, 2, 9, 11, 5, 6, if I throw in another 2, suddenly now there is a mode value for this set. Every value shows up exactly one time, except for 2. The value 2 shows up more than once. It shows up twice. That makes the mode for this set 2. The value 2 is the mode that shows up twice. Sometimes you can have a double mode. Let's see if I can do this without having to scroll down. So suppose I have the set 2, 9, 11, 5, 6. I have that additional 2, and I have an additional 11. Now I can say the mode for this set, it's bimodal. And the mode would be 2 because I have two 2s. And the mode would be 11 because I have two 11s. So that's bimodal. If I threw in one more 2, let me change color for that. If I threw in one more 2, now the mode snaps back to being just 2. Because I have 3 2s, and even though I have a bunch of 11s by comparison to the other numbers, I only have 2. So for the mode, you're only looking at what shows up the most. And that is a kind of middle, by the way. In the arithmetic of calculating the arithmetic mean, the mode will pull data, the average, toward that value. And in the measure of the median, again, the mode will pull the median toward that value because you'll have more of them on this side that have that value. So generally small changes, but still something to look at. So why, you might ask, are we using 3 different measures of center rather than just one? And that would be an excellent question. I'm going to try to clarify it a little bit. Suppose you go into a town and you take a really good random sampling of 30 individuals in that town, and you find that their average height, so you calculate the average or the mean, of all the heights in the town and divide by n, and you get 65 inches. 5 foot 5 inches tall is the average. And you put onto a frequency distribution, you put all of the heights. So you've determined that the average is here around 65, and then everybody else's heights kind of branch off this way. So you have a nice symmetrical distribution where right here in the middle is the median. And say the median is actually 64, some number close to 65 inches. That means this value is 64. And notice that for my data set, my median and my mean are relatively the same. The number of individuals that are on the right-hand side or shorter than 65 inches, and the number of individuals, 64 inches, the number of individuals that are 64 inches and shorter fall on one side, and the number of individuals that are 64 inches and taller fall on the other side. And it just happens that the arithmetic mean falls in exactly the same position as the median, exactly in statistical terms. So you'll see symmetric distributions like this when the mean is a really good measure of the center of data. But what if one day Kobe Bryant decides to move to this town? What are we going to get now happening? Well, our bigger than and little than, right? Our median isn't going to change very much. It doesn't matter how big, how much bigger than 64 inches people are on the right-hand side. It just matters that they're bigger than 64 inches. Kobe Bryant is definitely bigger than 64 inches. I don't even know his actual height. I think it's like 6'7". So, but it's still just bigger than 64 inches. So the median isn't going to change any. But what is going to change is by throwing one person that is way over here in height, the number of people that are way over here. This was a bad label I'm recognizing now. This just tells me how many people fall around 64 inches. And the greatest number of people are going to fall kind of there in the average. Initially, before Kobe, we had a nice, pretty, symmetrical distribution. And the histogram showed that beautifully. After Kobe comes in, though, the whole thing changes. His height averaged into our mean is going to push forward the average height of our sample set. And when we trace out our chart, when we trace out our curve, our bell is going to skew a little bit at the top, but a lot at the bottom to include his crazy height. Kobe in this case would be called an outlier. And outliers have a huge effect on the mean, but only a small effect, if any, on the median. And this is very useful information because we don't always want to make a frequency distribution histogram, and we don't always want to try to sketch in what we think the normal curve would look like. So we can compare two pieces of data and be able to predict the amount and whether or not there is a skew. So for example, suppose I have a set of measurements and I calculate that X bar is 48.6 and that the median, which is really just M, is 48.3. Because these values are so close together, I can say that this is a nice symmetrical normal curve. Or suppose X bar is 48.6 and the median is 38.1. This is a pretty substantial difference between the two. And I can say that the curve is going to skew. So the median is smaller than the average, which means that I have a positive or right-hand skew. And similarly, might as well just make all three examples. X bar is something like 8.6 and the median is 10. So if I were to make a frequency distribution histogram and I found that the median falls here at 10, but X bar falls over here at 8.6, then my bell curve is going to be relatively unaffected on the right-hand side. And more greatly affected here on the left-hand side. So I'm going to get this region of skew on the left-hand side. So I get a left skew.